Hello everyone, I am Krishna Kishore, Professor in Mechanical Engineering. Today in this session we are going to discuss the types of phase diagrams. So what are the various phase diagrams available and the features which are existed in phase diagrams. So we are going to discuss all these things in this session. Now, let us discuss the types of phase diagrams. Before going to decide or before going to understand the phase diagram, the conclusions of phase diagrams, let me discuss the phase first. So what do you mean by phase? A phase can be defined as a physically distinct from other phases and chemically homogeneous and mechanically separable portion of a system. So this is very important definition with which we can understand what is a phase here. Here the phase, if you want to say anything as a phase, it must be physically distinct from other phases. Suppose if it is a liquid is different from the solid, liquid is different from gas. So like that it is a physically distinct from other phases, chemically homogeneous, and with the help of formula, with the help of atom size, we can distinguish the whether it is a chemically homogeneous or not, and mechanically separable. So with the help of naked eye, we can say that whether it is a separable portion or not. So it is a mechanically separable portion of a system. And then when two phases are present in any system, it is not necessary that there will be a difference in both physical and chemical properties. So sometimes if two phases are existed, they may be same physical properties and same chemical properties. So that type of systems may present in the system. Then here, before going to understand the phase diagram is bound with the various rules. One of the rule is the phase rule here. So that means in a system, what do you mean by Gibbs phase rule? Here the system says that it is system under a set of conditions, number of phases exists can be related to the number of components and degrees of freedom by Gibbs phase rule. So means the phases, the number of phases is depends on the how many number of the components existed in the phases. And what about the degrees of freedom? So it depends on, so here the formula P stands for phase, F stands for degrees of freedom, and C stands for number of components. So with the help of this formula, we can decide how many number of degrees of freedom for a particular phase or for a particular state. So let us discuss the various phase diagrams and how they are classified. Let us discuss here. And the phase diagrams which are going to discuss now are classified according to the number of component present in a particular system. So how many number of components are existed? So depends on the number of components, the phase diagrams are classified. So that means sometimes a binary classification, sometimes ternary classification, etc. And the main classification is it depends on the composition and depends on the solvation. So the main classification that we are going to discuss now is this is the type 1 classification, which are represented as a type 1, means if two metals are completely soluble in liquid state and solid state. So that means in both liquid and solid state, if two metals are completely soluble, then that type of phase diagram is represented as a type 1 phase diagram. The second type is the two metals completely soluble in the liquid state completely, but and insoluble in solid state. If it is insoluble in solid state, but if it is soluble in liquid state, then that type of phase diagram comes under type 2 phase diagram. The next one is the type 3 phase diagram. What do you mean by type 3 phase diagram? Type 3 phase diagram means the two metals completely soluble in liquid state and partially, in the earlier case it is insoluble, but here it is partially soluble in solid state. If this is the case, then we can say that that comes under type three phase diagram. So let us discuss all these phase diagrams, and all these phase diagram depends on the solvation. So whether it is completely soluble or partially soluble in liquid state or in solid state. So let us discuss the type 1, which represents the two metals completely soluble in liquid state and solid state. So if you want to get the phase diagram, first of all we have to collect the data, which is represented as a cooling curve. So this is the cooling curve here. Observe the cooling curve first. This cooling curve means temperature E on y-axis, the time on x-axis. At various times, uh, the compositions, at various compositions, the cooling curves are drawn here. This is the 100, 0 means this is the pure metal. So that means there is no second material here. For this material, for the pure metal, if you draw a cooling curve, here it is a straight line. You can observe a straight line at the freezing point. This is the solidification point here, and this is the solidification. So this is the solid state. So means this is the solidification starting point, this is the solidification ending point, and like this. This is the end point here. This is for pure metal. If you consider the next one, this is 80 20. 80 means 80 is the matrix composition, that is suppose assume as the first material composition. 20 is the second material composition. If this is the case, then the solidification line, that is when this is the liquid line, is the freezing starting point or solidification starting temperature. T1 is represented as solidification starting temperature, and this is the solidification ending temperature. So if you consider all these things, 60 40 or 40 60 20 80, finally again the pure metal. So that means this is the graph for the B metal. So again you will get a horizontal line for pure metal like this. Now, so this, if you draw dotted lines for all the solidification starting points like this, you will get a curve like this. So this curve represents the solidification starting points, and if you draw a dotted lines, that is a curve for solidification ending point, so this curve represents the solidification ending point. So that means you will get this type of curve. So this is the data, the first we have to do for collecting or to draw a phase diagram. So in this manner we will collect the data. So this diagram shows the series of cooling curves for different alloys in a completely soluble system. Completely soluble system means here it is both in liquid state, that is soluble in liquid state, and solid state. So this is the diagram, this is the cooling curve for this type 1 phase diagram. So after collecting this data, we have to impose in phase diagram. Phase diagram consists of temperature versus composition. If you observe the x-axis here, this 10 20 30 40, so all these things represents the composition of the B, or in another word we can say that it is the weight percentage of the B. Whatever the data that we have collected with the help of various cooling curves represent on this curve, that is the temperature on y-axis and the composition on x-axis. If you draw the curve, so you will get the curve like this. You will get the curve like this, and this curve represents the three regions here. This is the first region, which is represented as a liquid, and you can see the just a picture, an image shows that this particular area shows the liquid, and in between these two curves, this line is a curve here. This curve is represented as a liquidous line. This curve is represented as a liquidous line, which is represented as a dash, starting at a dash, and assume this as B and B dash. So A dash, B dash, capital B dash is represented as a liquidous line. So that means the upper curve of the graph is represented as the liquidous line. And in between this, so that means between these two curves, whatever the region you have observed, this region is liquid plus solid region. So that means some hot metal is still existed and it is going to be converted as a solid. So that means solidification is happening. and it is at the middle. After that, this curve is stating the solidification ending temperatures, or this is the solidification ending curve here, and this curve is represented as the solidus line. So that means the area or the line or the curve between liquid plus solid region to the solid region is represented as a solidus line. So you can observe here, in between this region some crystals are available and they are converted into the grains like this. So that means a total solid is formed at the room temperature. So these are the information about the type 1 phase diagram, which says that if two metals completely soluble in liquid state and solid state, there exist three regions here. One is liquid, liquid plus solid, and solid region. And the two lines are available. One is liquidus line and another one is solidus line. So this is about type 1 phase diagram. Now let us discuss the type 2 phase diagram, which says that if two metals completely soluble in the liquid state and completely insoluble in the solid state. Completely insoluble in the solid state means you will get this type of phase diagram, which is also represented as eutectic type phase diagram. So let me discuss the various areas that here it is showing the various areas here where the various lines. Let me discuss in detail. Anyway, this is the phase diagram which is drawn in between temperature versus composition. The x-axis represents the 20, 40, 60, 80, 0. So all these are represent the weight percentage of B. Now, observe the line here. First of all this one is the liquid region, that is the liquid solution, is the liquid solution area. Hot metal, it is cooled. When it is cooling slowly at various composition, you will get this type of line. It's starting from M. So this starting point is the melting point of the first material, that is A, and the line comes like this, ME. This point is represented as a eutectic point. Eutectic points means at which the liquid is going to convert as a two solids. So that means solid A and solid B. So that means if you write a equation, liquid gives solid A plus solid B. So then that type of point at which it occurs is represented as a eutectic point, and at which temperature the eutectic point is existed is represented as eutectic temperature. So this line represents, if you draw a horizontal line at this point, this line represents the eutectic temperature, and whatever the Li is existed, this horizontal, there is a vertical line, dotted line, suppose assume as a 60% of the B. This alloy is represented as a eutectic alloy. So this is about eutectic, and whatever the solid, whatever the mixture, that is solid A and solid B, that we are going to get, all these are eutectic solid or eutectic mixture. So this is eutectic mixture, this is eutectic point, this is eutectic temperature, and the equation is liquid gives two solids, solid A plus solid B. If you observe the total phase diagram, you are observing the four areas here. One is, this is a single region, that is the liquid region. Left side, this is the liquid plus solid A region. Right side, that is the liquid plus solid B region. This region is represented as a liquid plus solid B. So the B percentage is more here. And if you observe after the eutectic temperature, whatever the region that you are seeing, this is a eutectic mixture. This is a eutectic mixture. So that means completely solid here. This is a solid region. Liquid plus solid B, and solid A plus solid B. So this is type 2 phase diagram. So here at various compositions you will get the different type of alloys, and with this phase diagram anybody can identify at what temperature, suppose what is the state of the alloy, whether it is in the form of liquid plus solid or whether it is in the form of liquid. Suppose if you assume for this alloy, that is a 20 composition, A is say 80 and B is 20. So that means A 80, B 20. For this alloy, we can say that at a T1 temperature, it is about to solid. So that means a few crystals, a few solid crystals may be formed at this temperature. So this is about type 2 phase diagram. If you observe the other phase diagram, that is the next phase diagram, type 3 phase diagram, two metals completely soluble in liquid state and partially soluble in solid state. Let us see the image of this phase diagram. Observe carefully. Here the various alloys have been shown here just for understanding purpose, and the regions are like this. This region, the top region, is represented as a liquid region. Anyway, this phase diagram is drawn between temperature versus composition, that is the weight percentage of B. And the top portion is represented as a liquid phase, that is a single phase. And this phase is represented as a liquid plus alpha. Alpha means the first solid, second two phases here. And the right portion, this portion is represented as a liquid plus beta. Here also two phases. At the left extreme position, observe this one here. Observe this one. The left extreme position is represented as the alpha region. That means single phase. Again, this is a single phase. And the right extreme position, observe this region here. This region again extremely related to beta. This is related to beta. So this is alpha, this is the beta region, single solid region. And here, so that's why it is a partially soluble in solid state. And this is two solids here, that is both alpha and beta are existed. Now let me discuss the various lines existed here. This line, it is started at a TA, and this line it goes like this, TA, E, and TB. So this line is liquidus line. Liquidus line means about to start of the solid crystal. So here after this point in any alloy, suppose for alloy 3 at a T3 temperature, the solid crystals are started. So that means up to this it is in the form of liquid. At T3 temperature for alloy 3 and at this compositions, assume that 60-40, 60 is A, 40% is B composition. At this temperature, at T3 temperature, the alloy is going to form the crystals. That is the starting of solidification at this temperature. For alloy 4, T2 is the starting temperature of the solidification. For Li1, T1 is the starting temperature. If you observe the Li2 here, we have to wait up to this temperature for solidification, and this is represented as a E. E means eutectic, the liquid. If in any particular case, if liquid is converted as a two solids, then we can say that it is a eutectic point. This point is eutectic point at which liquid is converted to two solids, and this line is called as eutectic line. And whatever the mixture that we are going to get after this line, that is under this line or the below this line, this mixture is represented as eutectic mixture. Both alpha plus beta phases are existed, but the left side of the region is along with eutectic mixture, alpha percentage is more. On the right side of the portion, along with eutectic mixture, beta percentage is more. And next one, this is liquidus line, and this is solidus line, that is F, E, and G. F, E, G is represented as solidus line. And two lines you are observing here, that is assume that as F, H here, and G, J, G, J here. So these two lines are represented as a solvus line. So totally different types of lines are existed in type 3 phase diagram. Let me repeat. The first line, that is nearer to the liquid phase, is represented as a liquidus line, that is TA, T suffix A, and E. TB. This line is liquidus, and this line, whatever the line here, that is a horizontal line at eutectic mixture, is represented as a solidus line, and below this solidus line the mixture is represented as a eutectic mixture. And these curved lines, that is assume as F, H and G, J. These two lines are represented as a solvus lines. So this is all about type 3 phase diagram. So totally 3 phase diagrams are existed. In this video, we have discussed 3 phase diagrams, that is type 1, type 2 and type 3 and their features. I hope you have understood. In next coming videos, we will discuss some more topics in material technology. Thank you. Thank you, one and all. I am Kakarla Krishna Kishore signing off.